Today we're going to be talking about inverse variation and reciprocal functions. Inverse variation is something that you might have seen before, actually, possibly in Algebra 1. Actually, I can almost guarantee that you've seen it in a science class at some point. So first of all, inverse variation is a relationship between two variables such that as one variable increases, the other decreases proportionally. That's important. It's just not one increasing and one decreasing. It's as one increases, the other decreases proportionally, meaning as one increases, the other decreases at the same rate. So this time it's going to be a good reminder to go and make sure your phones are away. I'm seeing quite a few of them out right now. So let's go and put those down. Make sure you have a pencil. For algebra, the way that looks is y is equal to some value of k divided by x, where k is not equal to 0. Because if something is increasing and decreasing proportionally, well, we'll talk about that in a second. In terms of our graph here, this is actually a graph of an inverse function. We got y equals 1 over x. It's kind of the parent function for an inverse function. And there's a new word here, asymptote. Anybody familiar with the word asymptote? It says one's at x equals 0 and the other is at y equals 0, which is a horizontal and a vertical line respectively. So with the x equals 0 asymptote, I'm just going to go ahead and do blue there. And I'm just going to drop a blue dotted line vertically because that blue vertical line right there, that is the asymptote at x equals 0. The one at y equals 0, I'm going to do in red. And it's going to go across this way. There we go. So an asymptote, just so you know, so you're aware here, when I use the word asymptote, or when we use the word asymptote in this class, it just means it's a line that your graph will get infinitely close to, but never actually equal. So for example, as the graph goes towards the middle, so as it goes down this way, and it goes towards the y-axis, it will never actually reach the y-axis. It's going to get closer and closer and closer and closer and closer. Same thing over here. As it ends up going up this way, it's going to get closer and closer and closer and closer, but never actually reach it. So this graph, the value of x will never equal 0. It will get infinitely close to 0, but never actually equal 0. So there's an asymptote at x equals 0. And the same thing is true of the y-axis as well. As we go back here, it's going to get closer to 0, closer to y equals 0 from the negative perspective. It's going to come up and 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 never actually equal 0. Same thing as it comes down here. It'll come down and it'll get close to 0, but it'll never actually equal 0. So that will happen a lot when we have inverse functions. And this is another reason why k cannot equal 0 here. We'll talk about that more as we work through this. So over here, it says the reciprocal function. Let's talk a little bit more about here, and then we'll move on to some actual implementation of what we're learning. The reciprocal function models the inverse variation y equals 1 over x. Like other functions, it can be transformed. So transformations we've learned are things that either shift or stretch or reflect a particular function. And so you're going to see some familiar variables over here. So if you take a parent function, y equals 1 over x, and you stretch it, or not stretch it, but if you shift it vertically, that's going to be the value of plus k after the actual fraction, which is a rational number. So after the rational number, there's going to be a whole number added to it, maybe not even a whole number, but there will be a number added or subtracted from that. If it's plus, that means its graph has been moved up. If the k value is negative, it means the graph has been moved down. The h part. We've seen x minus h a lot, and you've seen it a lot since the beginning of the school year. The value of h is a horizontal shift. If it's a minus in the actual function here, that means it's moving to the right because the function itself has subtraction in it. So if h is positive, like in this example, if h is 4, that's a positive movement on the x-axis 4 spaces. So that would be 4 to the right, and k is equal to -2, so it's also been moved 2 units down. So it's basically taking And you can see that right here. Parent trace is transformed 2 down and 4 to the right. And if you take a look here, it's basically moving it, taking this exact graph, it didn't change the shape at all. And we took it 4 right and 2 down, moved it from the middle over and down, and now it's here. There are actually 2 asymptotes here. It only lists one of them. X equals 4 is one of them. And then the other one, does anybody know the other one? It has to do with the shifts. So X equals 4 is this one here. What's the other? It's going to be a Y equals. Or yeah, where's the other asymptote at? Y equals. How far down did it go? 2. So it's going to be Y equals -2. So it's the same as the shift, which is going to be this dotted line right here. So we got the horizontal asymptote and the vertical asymptote. Vertical one is X equals 4, horizontal one is Y equals -2. All right, so that's kind of like your basic setup here. Now, this next question is not going to seem to have much to do with the diagram and stuff that we just looked at. So I'm going to talk about how to figure this out here. So it says identify. Take a look. Identify. Determine if each table of values represents an inverse variation. How do you think? Actually, think back to the warm-up question with the area of the rectangle. How do you think we might be able to figure out if this is an inverse variation or not? And I'll put it in terms of this first question. If you multiply length times width, you get area, right? So if you imagine the length or the width, length and width is X and Y. If you imagine length and width is X and Y, what could you do with the values of X and Y to figure out if this is an inverse variation or not? What happens when we multiply the length and the width together of each of these from A? What's the answer? 144, right? So if you multiply length and width, you get 144. That's the same idea here. Imagine if 1 is the length and 25.5 is the width. What's the area? $25.5, yeah. So what we're looking for here is a proportional relationship when you multiply the X and the Y values. They should end up equaling the same thing. Because if it's an inverse variation, one is increasing and the other is decreasing proportionally. The way that you can check to see if it's proportional is to multiply X and Y together. It's like multiplying length and width. If it's proportional, the length times the width, in air quotes, should give you the same area with each rectangle, right? We're not actually having rectangles here, but it's the same idea. So we're just going to make a third box underneath here. We're going to call this XY. And in that third box, we're just going to list off the product of X and Y with each box. And if even one of them is different, we can stop and say, no, it's not an inverse variation. If they're all the same, then we say, yeah, it's an inverse variation because as one of them increases, the other one decreases proportionally. So this first one we know has to be 25.5 because 1 times anything is that other thing. What is 2 times 12.75? Somebody do that for me real quick. 2 times 12.75. Is it? Same thing? Okay. 25.5. How about 3 times 8.5? I see a lot of calculators. Do the multiplication. What's 3 times 8.5? What is it? 25.5 again? Okay. What about 5 times 5.1? Yeah, 25.5. Okay. How about 6 times 4.25? Yep. Okay. And then 15 times 1.7. Does that work too? Okay. So that would be an inverse variation. So we'd say, yeah, because the product of X and Y all equals 25.5. So we can just say yes. Now, usually in these types of situations, there always seems to be an example and then a non-example. So if I had to guess, based on the fact that I've taught for a while and that usually problems like this do one of each, I'm going to assume that B is no, but let's prove it. So XY, what is 6 times 3.3? $19.8. Okay. What is 5.5 times 5? 27.5? Okay. So right away, the answer is no. Very quickly, we can find out that that is not an inverse variation. Maybe it's a function, but it's not an inverse variation function. So as soon as we get to a different number for the product, that's it. We're done. We say no. Okay. Questions about how to decide using a table if something is inverse variation? Pretty straightforward, right? Multiply if it's the same, yes. If it's not the same, no. Okay. Example 2. In an inverse variation, x is equal to 6, y is equal to 1/2. What is the equation that represents the inverse variation? So go back to the first page real quick. And somebody give me the function, the algebraic function for inverse variation. Not the parent function, but the algebraic. The standard algebraic without the shifts. Y equals k over x. Good. Now, we have a value for x and we have a value for y. So what do you think we're going to figure out here? What's that? Yeah, we're going to figure out k. If we plug in for x and y, that will allow us to solve for k. Once we have k, we can then write the function as an inverse variation using just x and y as opposed to the numbers for x and y. So plug in for x, plug in for y. So that's going to be 1/2 equals k over 6. Now, if you remember solving proportions, what do we do next? You remember how to solve an equation like this when it's written as a proportion? Fraction equals a fraction, or ratio equals a ratio. Does this look familiar? Cross multiply. So multiply diagonally across the proportion. 2 times k is 2k. 1 times 6 is 6. So what does k equal? K is 3. All right. K equals 3. Now all we have to do is substitute the value of k back into the algebraic function of inverse variation. Substituting k, leave x and y as x and y. So the answer here is going to be y equals 3 over x. That's the equation. Figure out b on your own using this function here. Using this function here, what is the value of y when x equals 15? Go ahead and do that real quick. All right, what do we get for y? When x is 15, what does y equal? 1/5, yeah. Plug in 15 for x, that's 3/15. 3/15 reduces to 1/5. So that's it. Okay. If we have time, we might come back to the habits of mind question at the bottom of the page here, but let's go ahead and keep working through the examples. So any questions so far? Seems this is kind of like algebra 1 type stuff right now. It isn't too bad. All right, flip it over. So this says we're using an inverse variation model, so it's going to be a word problem here. So the amount of time it takes for an ice cube to melt varies inversely with the air temperature in degrees Celsius. At 20 degrees Celsius, the ice will melt in 20 minutes. How long will it take the ice to melt if the temperature is 30 degrees Celsius? So we have to write an inverse variation equation for this, and then use what we have to go from there. So, what do we think? We're going to work through that one. Give it a try. If you need some help getting started, I'll give you a little hint here. You got to figure out what K equals, and then go from there. Anybody have an answer? Yeah. You nodded your head, Harry. Yeah. What did you get? 13.3. Okay. Cool. So we've got our function, right? Y equals K over X. Now, the nice thing here is that it doesn't really matter which number is X or Y when you're solving for K because, well, they're both 20. But if we read it in a certain way, at 20 degrees Celsius, the ice will melt in 20 minutes. So it depends on the temperature, how long it will take. So if we're talking about dependent and independent variables here, the dependent variable is x. The independent variable is the time. The time depends on the temperature. So we're going to plug in 20 for y, set it equal to k over 20 for x. I'm going to put a 1 underneath the 20 because there's no fraction that time. And then if we cross multiply, 1 times k is k, 20 times 20 is 400. So k equals 400. So the value of k then, which if you ever, anybody here ever learn about direct variation, the y equals k times x function in science? Did you ever see that one? The value of k is known as the constant of variation. And so we'll just say, the constant of variation k is 400, which means that the function is y equals 400 over x. And if we're talking about degrees were our values of x. How long is it going to take if the air temperature is 30 degrees Celsius? Well, we're going to plug in 30 for x and then solve. So basically the problem turns into 400 divided by 30. So y equals 400 divided by 30, which equals about 13.3 minutes. Say approximately. That's our answer for that one. All right. I think we only have 2 more problems in terms of our notes, and then I'll have you try some of the work on the very back of this, and then I'll get you your assignment after that. So we're going to graph, we're going to figure out the domain, the range, the asymptotes, and then we'll go from there. So the thing that I usually think of when I'm working on problems like this is, first of all, let's go ahead and just get because we don't have any shifts going on, right? There's no value of h or k, so there's no horizontal or vertical shift happening. So we can just put our x and y axes directly in the middle. We don't need to move anything around. All right. And then we can use a table of values to figure out values of x and y. And then we can double check it using our graphing calculator to figure this out. So let's start with, let's see, what is this? 1, 2, 3, 4, -5. Okay. So if we go from -5 to +5, that'll be a good x, that'll be plenty of points to get a good idea about what this thing looks like. So we'll say xy, and then -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, and 5. So we're going to make a nice big table here. We've got 11 points that we're going to be able to get. And most of this, we should be able to get a lot of this just using mental math. So what is 10 divided by -5? Because if x is -5, what does y equal? What is it? 10 divided by -5? -2? What about 10 divided by -4? Feel free to use the calculator as well. That's fine. -10 divided by -4. You've all got calculators. Go ahead and somebody tell me. What is it? Yeah, -2.5. All right. 10 divided by -3. It should be -3.3. 10 divided by -2 is -5. 10 divided by -1 is -10. What about 10 divided by 0? What's that? 10 divided by 0. What's your calculator say? Should give a domain error, right? Okay. I'm going to put a red X there because there is no value. You can't divide by 0. That's not a mathematical possibility. X cannot equal 0. which is a hint about where an asymptote might be. So let's keep going. 10 divided by 1 is 10. 10 divided by 2 is 5. 10 divided by 3 is about 3.3. 10 divided by 4 is 2.5. 10 divided by 5 is 2. So those are our values of x and y. So we can go ahead and plot those. So -5, -2 is here. -4, -2.5 is about right there. -3, -3.3 is about here. -2, -5 is here. So we don't actually have -1, -10. If we counted by twos, we could fit some more points on here. But we'll just do something like that for now. And then we're going to have 110. We can't fit that on it. If we counted by twos, we probably could. 2, 5, that's here. 3, 3.3. About right there. 4, 2.5 is there. Or sorry, 3, 2, 5. Oh, wait, nope. All right, sorry, I put that in the wrong spot. 2, 5. 3.3 goes there. 4, 2.5, and then 5, 2. So that'll come along like this. Okay. That's going to keep going down that. So this is a little more spread out than what I would have wanted. So if I were to redo this, I'd probably go by twos on my x and y axis. But we can take a look at the function on our graphing calculator anyway, and then it'll give us an idea about what we're looking at. So we're going to have 10 over x. Then we can take a look at our function. I need to put some points out of there. Let's see. Go to my list. Clear those out. Clear those out. All right. Back to the graph. Invalid dimensions. What are you talking about? Okay. There we go. So there are some things that we need to make statements about as well. So yes, we graphed it, but we also need to say what are the domains, ranges, and asymptotes of this function here. So let's start with our asymptotes. I'm just going to write ASYM for asymptote. There will be an asymptote for x and for y, because you can see that it's getting closer to a certain value of x and it's getting closer to a certain value of y, but it'll never actually reach it. So if we look at our graph here, I'm going to zoom out just to get a bigger view of what's going on here. There we go. This looks a lot better. So the value of x that it's approaching but not actually equaling is what? Who can tell me that? How close? So as the graph approaches, it gets closer and closer to x equals 0, but it doesn't actually reach it. Same thing from this side. It's going to approach x equals 0, but never actually get it. That means one of our asymptotes is at x equals 0. The other one, it is approaching is y equals 0, but never actually reaches it. And it's approaching it from the bottom, but it's also approaching it from the top, but it will never actually equal 0 either. So the other asymptote will be y equals 0. All right, now we got to talk about domain and range. So the domain and the range. So the way that this works is anytime we're talking about domain and range, we're talking about all possible values of x and y. That's what domain and range means. Now, there's only one number in the domain that doesn't work. What is it? There's only one value of x that cannot be calculated here. What is it? It's 0. Likewise, there's only one value in the range that it doesn't work for either, or it can't equal, and that's also 0. Wherever you have an asymptote, I just want to make sure everybody's clear on this. Whenever you have wherever you have an asymptote, the value of x cannot equal that value, and the value of y cannot equal that value, because it never actually equals that value. It gets infinitely close to it, but it will never equal it. And so if you're talking about domain and range, you cannot include those values in your domain and range because they're not part of the domain or the range. So the domain here is going to be, we're going to say all real numbers, comma, x is not equal to 0. There's a limit to what x and y can equal. And then the same thing for the range as well. The range goes up forever, it goes down forever. The only value it doesn't work with is 0. So we're going to say the range, and then y does not equal 0. So all real numbers for the domain and the range, except for when x equals 0 and for when y equals 0, because those are not possible. All right. Let's try the next one. Actually, I'm going to have you try the next one on your own. But I would like you to make a scale factor of 2 for each line on here. So you can put your x and y in the middle if you want to. Although I'm going to move it to the left one. From the middle, and let's see, +2, move up a couple. So I'm gonna go down one as well. Let's do this. But I'm still gonna count by 2s on my x-axis and my y-axis. So we'll be able to get a little bit more detail on there. Now, what you are welcome to do, now that we've done everything by hand here, you're welcome to just graph this on your calculator and then go to the table of values and put the points in that actually you can fit on. So math fraction 1 over x minus 3, and then +2. And if we go to the graph, this one is not going to end up being perfectly centered. I'm going to zoom in on that. I'm going to go back to Z standard. That's number 6. Okay. So this is what the graph is going to end up looking like. And if you go to your table of values, I'm going to go back all the way to -10. And -10 says 25/13. So let's see. That's about 1.9. So -10, 1.9. So here's 2. So that's about right there. I'm counting by 2s each time. I'm going to go to -8 next. I'll just go by 2 each time. So then 21/11 is 1.90 as opposed to 1.92. So that's barely come down at all. That's still about right there. Go back to -6. That's 17/9. 17/9 is about 1.88. So that's barely down. Go to -4. 13/7 is 1.85. So that's barely down as well. -2 is at 9/5. That's 1.8. So again, not much movement is happening here. At 0, we're at 5/3, which is that's about 1.7. So that's dropped down a bit right there. Because we're going by 2 each time here. So that's going to go down below halfway. At +2, we're at 1. Oh, sorry, 1.7 is up here. 1 is here. I was thinking 0.7. 4 is at 3. So let's see. Oops, hold on. 0 is at 5/3. 2 is at 1. So 2 is there. Sorry. 4 is up at 3. So 4 is at 3. 3 is right here. I'm going to cross that off. I'd stop going by 1s for a second. Okay. That crosses off it. Okay. 4, we got 5, and then 6 is at 7/3. So 7/3 is 2.3. So 6 and then 2.3. About right there. 8 is at 11/5. 2.2. That's coming down a little bit like that. 10 is at 15/7, which is 2.1. That right there. And then 12 is getting even closer to 2. So we have ourselves, if we go back to the graph real quick, where does it look like this vertical asymptote is? The horizontal one is definitely at 2, right? Y equals 2 for sure. We definitely have one at y equals 2. Right there. That's a horizontal asymptote there, but the vertical one seems to be somewhere in between 2 and 4. Yeah. Is it 3? Okay. How do you know that? There you go. Halfway in between 2 and 3. Let's move it over to the right 3. So if we go halfway in between 2 and 4, that puts us at 3. So our vertical asymptote is here. So what we end up with, if you look at the graph on the calculator, you can go ahead and just kind of follow what's going on here. And that is going to come and it's going to basically turn very sharply and end up going down like that. And then this one's going to stretch out over to the left there. And then this one is going to have a very sharp curve right here. And then it's going to come down about like that. So this is what our inverse variation looks like here. So on this one, it's asking, what are the equations of the asymptotes? Okay, so the asymptotes are at, we've got x equals 3, and we have y equals 2. Those are the asymptotes. X equals 3 is the vertical dotted line here. Y equals 2 is the horizontal dotted line there. The domain and the range. So the domain, all possible x values except for what? 3. So all real numbers, comma, x does not equal 3. Last time it was at 0, this time it's at 3. How about the range? All real numbers except for y equals what? What was it on this one? How high up is it? 2. Yeah. So graph, asymptotes, domain and range. Here's a quick question for you. A translation of the reciprocal function has a vertical asymptote at x equals 5. What are the possible equations for the function? So by the way, the reciprocal function is the one that we saw on the front page here. It was y equals 1 over x. What's a possible equation for this if it's been translated, or sorry, not translated, if it has a vertical asymptote at x equals 5? What could we write for an equation? This one has a vertical asymptote at x equals 3. So maybe use that equation and then write something, or tell me something similar that we can do for this one. X equals 5 means it's been translated which direction? Left or right? If it's a positive 5, has it gone left or has it gone right? Which way is positive on the x-axis? It'll be right 5. And this one has been moved right 3, and it shows that with x minus 3 on the denominator. So we could just write f of x is equal to 1 over x minus 5. That would be a shift of 5 units to the right, which would give us a vertical asymptote at positive 5 on the x-axis. So I'm going to look at the back questions here real quick. I'm just going to decide if there's anything important that I need you to go ahead and okay, just verbally real quick. Number 3. We don't need to write this down, but I do want to talk about this real quick. On the very back question number 3. All right, listen up, guys. Question number 3 on the back. We just need to talk about this real quick. I don't need you to write it down. But why is it impossible for the function of y equals 1 over x to intersect the horizontal asymptote at the x-axis? Why can this graph not intersect the asymptote? Yeah, and listen up. That would also defy the definition of an asymptote. Because an asymptote is, by definition, something that cannot be intersected with that particular function. It will get infinitely close to that, but it will never equal that. And in order for something to intersect, it has to equal that value. So this would actually betray the definition of what an asymptote actually is if that function could intersect with the asymptote. So those two things are at odds with each other. So that would be why. I wrote your assignment on the back here. It is pages 187 to 188, 8 through 26. It's all of them. I printed them out as well. So you are welcome to, let's